Welcome to Chapter 5. So far in this series, we've been living in the world of abstract ideas, looking at the logic of AI models. But today, we're going to get physical. We're bridging the gap between pure theory and the hard reality of silicon, memory, and power. The actual stuff these models have to run on.
So let's kick things off with a question that's honestly a bit of a paradox, one you probably deal with every single day without even thinking about it. How can a model that was trained in some massive data center, a place that's sucking down enough energy to power a small city, somehow end up running on your phone and give you an answer in like a split second? How is that even physically possible?
Well, the answer, as you might guess, isn't magic. It's really a story about some incredible, relentless engineering. And that's our theme for today. The biggest story in AI right now. It's not about building these ever bigger digital brains. It's about all the clever, often totally invisible, work that goes into making them efficient enough to actually be useful in the real world. Okay, so here's the plan. We're going to start by looking at the two very different worlds an AI lives in. Then, we'll dive into the engineer's toolbox. We're talking about things like quantization and a really clever technique called LoRA. We'll also see how smaller, really capable models are born and even how to make them generate text faster. And we'll wrap it all up by getting to the heart of the matter. What's the real bottleneck holding all of this back? All right, first things first. If we really want to get a handle on efficiency, we have to understand this fundamental idea. Every single AI model out there basically lives a double life. It operates in two completely different worlds. On one side, you've got training. You can think of this as the discovery phase. It's a brute force, super energy-intensive process where the model figures out its parameters by churning through mountains of data. We're talking weeks, maybe months, and millions of dollars. But then, on the other side, you have inference. This is the model in action, the one you actually interact with. And here in the real world, efficiency isn't some nice-to-have feature. Nope, it is the absolute #1 requirement. Okay, so you've got this massive model that was born in a data center. How on earth do you get it ready for the real world, for inference? Well, the first, and maybe the most straightforward way, is to just squeeze it down. Make it smaller. This whole process is called quantization, and at its heart, it's a really simple idea. You just reduce the precision of the numbers the model uses to store its information. Instead of using a super detailed number with lots of decimal places, you use a simpler, less precise one. And the reason this works, which is kind of amazing, is that these networks are incredibly robust. The knowledge isn't stored in one single perfect number, it's spread out across millions of them. So a tiny bit of rounding on each individual number, it barely makes a dent in the final answer. And this right here shows you the trade-off in action. Your standard 32-bit number, what we call a float, it can represent a mind-boggling range of values with insane precision. That's what you need for training. But an 8-bit integer, it can only represent 256 different values. That's it. So what you're doing is trading away a level of precision that, frankly, you probably won't even notice for a massive win. We're talking a 4 times smaller model, and it's way faster to compute, because simple integer math is a walk in the park for a processor compared to floating point math. But here's the thing, quantization isn't just an on or off switch. It's more like a whole spectrum of choices, a whole toolkit for an engineer. You can see here, you've got everything from a fairly standard 8-bit version all the way down to these super compressed 2-bit schemes. As you go down the list, yeah, the model gets smaller and faster, but you start to run the risk of losing some performance. So picking the right one is a huge part of the job. It's all about balancing the hardware you have with the quality you need. Okay, so you've done all this work to shrink your model. Now what? You need a way to actually package it up and send it out into the world. And that's exactly what something like the GGUF format is for. Just to be clear, GGUF isn't the model itself. Think of it more like the perfect shipping container. It holds all the compressed parts and the instructions, making it super easy to load and run these optimized models on pretty much any kind of system. Right, so the model's smaller now. That's great. But what happens when you want to teach it a new trick? Adapt it for a very specific job. Does that mean we have to go back to square one and do that whole expensive training thing all over again? Thankfully, the answer is a big no. Fully retraining a model, what we call fine-tuning, is just way too expensive for almost anybody. It would kind of defeat the whole purpose of making things efficient. So naturally, engineers came up with a much smarter approach. And that solution is a set of techniques called parameter efficient fine-tuning, or PEFT for short. The core idea behind it is just brilliant. It's this. Instead of messing with all, say, 10 billion parameters in a giant model, what if you could get the exact same result by just tweaking a tiny fraction of them? Maybe just a few million, or sometimes even less. And the most popular way to do this is a method called LoRA. Let me walk you through how it works. It's super clever. First, you take that massive original model and you freeze it, lock it down. None of its original programming is going to change. Then, you inject these tiny, new trainable modules into a few key spots. And then, this is the important part, you only train those little new pieces on your new data. What you end up with is something like a behavioral overlay. You've changed what the model does without ever touching its core foundation. It's like surgical modification for AI, and it's incredibly cheap and effective. So LoRA is fantastic for tweaking the big guys, but it raises a good question. What if we didn't even need the big guy to begin with? What if we could build a powerful, expert model that was just small right from the get-go? And that brings us to this really cool process called knowledge distillation. The idea is you take a massive, super powerful teacher model and you use it to train a much smaller student model. But here's the key. The student isn't just memorizing the teacher's answers. It's actually learning to mimic the teacher's thought process. It's learning the probabilities and the patterns the teacher uses to get to an answer. It's learning the how, not just the what. And this whole technique has given rise to this new wave of what we call small language models, or SLMs. You see models like Phi-3, which has around 3.8 billion parameters, but it can hang with models that are 10 times bigger on certain tasks. These SLMs are perfect for running on your phone or in your car, and they prove a really fundamental point. Bigger isn't always better. Capability is not just about size. A smart design and great training data can pack a huge punch in a small packet. Okay, this last technique we're going to talk about is a little different. So far, we've been about making the model smaller or training it more efficiently. This one is all about speed. It's about changing the very process of how the model generates an answer to make it fundamentally faster. It's a method called speculative decoding, and it works by using this really clever two-model team. You've got one small, super fast draft model. Its only job is to just race ahead and guess the next few words in a sequence. Then the big, powerful target model comes along behind it, and in one single parallel step, it checks all of those guesses at once. It's like having a scout run ahead and the main army following up to confirm the path. Now, the key to making this whole thing work, to making it fast, is making sure that little draft model is a really good guesser. The better its guesses, the faster you go. And so you have methods like AdaSpec that are designed to do just that. Instead of trying to make the small model good at everything, you just train it to be an expert at the easy stuff, the really common words and phrases that it's almost guaranteed to get right. And the result, as you can see, is a much higher acceptance rate. When the big model can just approve, say, 80% of the little guy's guesses instead of 65%, the whole system just flies. You end up getting the best of both worlds. You get the high-quality, nuanced output from the big, powerful model, but you get it at a speed that's much closer to the little, fast one. It's a pure win from a clever algorithm. Okay, so let's take a step back. We've talked about quantization, about surgical fine-tuning, knowledge distillation, speculative decoding. These are all seriously clever software tricks. But what's the deeper reason they exist? What's the fundamental, physical problem that every single one of them is trying to solve? The answer is simple, and it's physics. The real roadblocks for the future of AI aren't just about finding a better algorithm. They're about the hard limits of the physical world. Things like memory bandwidth. How fast can you physically move data around? Energy consumption, heat, and maybe most importantly, just how long a person is willing to wait for an answer. Every single trick we've looked at today is, at its core, a way to work smarter within those unchangeable physical laws. And that brings us to the most important takeaway from all this. The next huge breakthrough in AI, it might not be some new model with 1 trillion parameters. It's just as likely to be some quiet, brilliant piece of engineering that lets the models we already have run twice as fast, on half the power, right on the phone in your pocket. Because at the end of the day, progress in this field isn't just about building bigger brains. It's about the relentless, difficult work of making them actually work in our world.